Last topic in this introduction to statistic part is linear regression model. Linear regression model is constructed, or the estimation of unknown parameters in linear regression model is done by using the LM function. So if we have this sort of a response variable y, which is assumed to be linearly dependent on some explanatory variables x1, x2, all the way to the xk, where all these beta values here, they are some unknown parameters, and this is some sort of random error term. Then we can use this LM function to estimate these unknown beta parameters, and this way to get out this sort of a linear regression equation, which is kind of give us the estimates for the mean value of y, that is the expected value of y. After using this LM function, then we can use this sort of function as sigma to understand how much there's a variation in what is the standard deviation of this random error term. And then there's this sort of VCO function, which gives us the estimates for the covariance matrix of estimators of these beta parameters. And well, we can use that if we need to do some sort of a particular test statistics, but in everyday use you may really need less this than this one. And then there's this sort of a basic function like fitted and residuals, which are given the fitted values and residuals of the models, and based on these values we can then evaluate if the model is fits the data sufficiently enough. Part of the linear regression model is for prediction or estimation of the expected value, and this can be accomplished by using the predict function, where we need to give this sort of a new data, which is like values of some xi star values, that is the what is the condition, what is the situation, what are the values of explanatory variables, under what condition we want to make the estimate for the expected value. And if we use this sort of argument that interval is confidence, then we are really calculating the just not the point estimates for the expected value, but also the confidence intervals for the expected value. And if we then in a predict function we start to use the word prediction, then we are now then getting the point prediction for the new observation, or this sort of observation which has been given the x values, but also the prediction intervals for this new observation. And finally, a useful function is obviously, again in a linear model, is ANOVA, which kind of in regression models it can be used to perform the F test for comparing two models. So here in the code I have created this sort of artificial data in a way that I have first generated 54 observations from uniform distribution from 1 to 100, and I have rounded up those using the round function to those generation to the just 2 decimals, and same applies to the x2 vector. And then I set these sort of a beta values, so I try to kind of generate or simulate the y values first before I start really do the modeling. So I use these sort of a beta values, and then I create this sort of a mu vector, which is now beta 0 plus beta 1 multiplied by our x1 vector plus beta 2 multiplied by x2 vector, where the beta has been set this sort of values. This is a -2, by the way, the beta 2. And after we have this sort of expected values, then I create this sort of a random variables y, or the realization for the random variables y from normal distribution, with the expected value being this mu value, which has been now calculated or construct here, and then the standard error of a random error term is assumed to be on level 30. And we can then use the plots to see what sort of a data is, but in the end we want to do the modeling, and then we kind of want to do models so that we think that yi is equal to beta 0 plus beta 1 multiplied by x1 plus beta 2 multiplied by x2 plus random errorness, in this case when we have two x variables. And by using this sort of form, or use the ln function in this way, so that we put our response variable y there, then we put this Worm side basically, then x1 plus x2, we get our model estimation bit done, and then by using the summary we get this sort of output, which is now basically giving us the estimates for this intercepts and beta 0 ones and beta 1 and beta 2 values. As you can notice, we have ourselves set these values for beta 0, beta 3, beta 2, beta 1, 2 and beta 2 minus 2. And when we have estimated, then based on the data, like beforehand, if we only had this data, what would be our estimates for beta 0, beta 1 and beta 2, we would get this sort of estimates. So in the case of beta 1 and beta 2 we get quite a good estimates, but for beta 0 our estimate is completely different than what is said in our model. And then we can use the sigma function to get our standard deviation of error, so that is called also residual standard error, which is given also here. Then if we need the covariance matrix of the beta vector hat, then it is given here, and then we can take fitted values and residuals, maybe do some plotting, and then we can start maybe calculating some prediction values or estimates, calculate the estimates for the expected value mu by changing, for example, the values x1 from, let's just say 1 to 100 with the integral values, and then keep x2, for example, in a level of 40 and 80, and to see what sort of estimates for the expected value we can obtain when x are set like this. And then we can also predict new observation with the x is set like in this level. And this sort of a result we can easily plot and get quite good understanding of how the model is behaving. And lastly, we considered a situation that what if we want to test is the, for example, x2 variable statistically significant variable. Then we basically do this sort of a model where we have where we explain the the y vector by x1 vector and leave the x2 vector out of the model. This is what is called like a more simple model. This is actually simple regression model in the sense that there's only one explanatory variable in a model, and then we do the comparison or the test should, okay, let's just say this way, if we use this sort of alpha function in this way, we basically are testing is the x2 variable statistically significant variable in a model, and basically we are then also same time kind of testing is the beta 2 parameter equal to 0 or not. And this is what we get. This is a f-test statistics, and this is a p-value which says that we should reject the null hypothesis, which is in this case the hypothesis that the x2 variable is not statistically significant factor in the model. And result is that it is better to use this sort of a linear model where we have both of these x's, x1 and x2 as explanatory variables. If we take a look at this code now, then we can first create our data set by using this sort of a way. So here we have, for example, x1 value has this sort of a value, this time x2 this sort of a value, and in the end y has this sort of value. So these are different values now that which were used during the estimation and this example code in this selection slice. Each time we run this code we get a different type of data, a little bit different kind of data. So after this simulation the plot would look like between x1 to the y as this way, and x2 it would be looking like this way, because there's a -2 really. The coefficient of beta 2 had the beta 2 is actually -2, because we know that if we use the co-plot we can get this sort of a result, for example, and then we can do the model. So the model is done in this way, and if you look at the summary we get these sort of estimates this time around. Seems like intercept is always estimated a bit biasly, or it does not really fit that well, or go to the level of 3. Well, we are not so worried about that. We can get a sigma that is the same value as here, and it means that it's a square root of variance of a random error term. So it's a standard deviation of the random error term, what we meant by this sigma value. And we can do some plotting about the fitted values and observed values. For example, it looks like this way. And fitted values with the residuals, we can do that sort of a thing to see if our model is really making any severe bias in some section of fitted values, but that's not really happening. Then we can do this sort of a new data, which is using by this expand grid value. We get our new data looks like this, so that there's like in two set of values for x2, like 40 and 80 time, we have x1 running from 1 to 100. And if we, in those sort of a situation, we estimate the mu hat values, we get this sort of a, by using this sort of a line. And if we use estimate, predict the new observation, then we should use this sort of a line. And if we start plotting the result of what we get here, then we could see that this estimation part of expected value, it looks like this in a case of x2 being set on a 40 level. So the line here is drawn in a case that x1 is changed from 1 to 100, x2 is kept on the level of 40, and then the regression line gives us the estimates for the expected value, which is now beta 0 hat plus beta 1 hat multiplied by x1 value plus beta 2 hat multiplied by x2 value. And x2 value here is all the time 40. And if we change the x2 values from 40 to 80, then the lines goes with respect to the x1 variable in this direction or here. And these are now the confidence interval lower bound and upper bound in these sort of cases. And if we continue with the prediction, then we can notice that in a case of x2 set on a 40 level, prediction intervals for new observation are between these red lines. And if we move to the case that x2 is set on 80, then these prediction intervals, there's some typo, sorry. Then the prediction intervals looks like this. So they are here and I guess here. So anyway, that's one way of looking at the result of these regression models. We can have these sort of models where we have only one explanatory variables like given here, and in the end, if we do this sort of a testing about the statistical significance of x2, then it's simply just comparing these two models and getting these sort of results. So we get a f-test value, which is our test statistic, and p-value, which is very, very small. So we would reject the null hypothesis that x2 does not have an effect on the average level of y, and alternative hypothesis is considered, and that's that x2 has a linear effect on the expected value of y. Now our last example is this example 2.3, where we consider this sort of a dataset black series, and this dataset provides the measurements of girth, height and volume of a timber in 31 felled black cherry trees. And we try to model the volume of the tree by this sort of a linear regression model, where there are these two, girth and height, are used as a explanatory variables. And then we ask what are the maximum likelihood estimates, that is, what are the estimates for these unknown beta parameters, and find some sort of estimates for this variance parameters related to this the random error term, and then we should find out point and confidence interval estimates for the expected value when the x are set on these sort of levels, and then do the same for prediction intervals, and then consider this sort of a hypothesis that we want to test if the x2 variable really statistically significant variable in this model equation. And if we now go to the code, then we first read this black cherry data here, and the data looks like this way. So this is our y variable, this volume, and then we can look how it behaves with respect to the x values. With girth, there's this sort of a strong linear relationship, or at least a relationship such that it could be at least we can consider modeling by linear model. And then with the height and volume, this overall picture looks like this way, or scattered plot looks like this way. Then we can do the model with using the LM function like this way, and we get a summary of model, which gives us then already the estimates for beta 0 hat value, beta 1 hat value, and beta 2 hat values. And now that we asked for these, what are these estimates, we can then use this sort of a coif function, which then also gives the estimates here as a numerical vector. And then if I take this sort of a function sigma and model, this really gives us the standard deviation of the random error term, and if we raise this to the power 2, in this way as given in the code, this is like the estimate, unbiased estimate for the variance parameter of the random error term. And in case of C, we set our new data in this way, so that we set the girth at a 30 level and height at a 22, then we put it as in a new data case, which is now having this sort of values. And then if we use this predict function with our model, new data is now this new data which we have set and put as an interval confidence, and if we set the level of confidence intervals to 95%, then we can get these sort of values, mu hat values, and here really we get the point estimate for this mu hat values in a case of x set as 30 and 22, and the lower bound here is here and the upper bound is here of this confidence interval. And if we do that same thing for new observation, then we change here in a predict function the interval as a prediction, and in that case, there should be new data like this way. Like this way. And now if I look the y hat values, then the fit, which is a point prediction, is actually same as the estimate of the expected value. However, if you look the lower and upper bounds of these prediction intervals, they are wider than in the case of estimation, which shows that there is this sort of a extra randomness which is needed for when we are predicting the value to be included in certain interval. Then we need to little bit make the intervals wider than in a case of estimation of like a population mean level, what is estimation of mu hat really is all about. So this gives us now this sort of a result as this way. And finally, we may now consider the question of is this height statistically significant factor, and this case we consider model where we have only modeling the volume by the curve. This is a one simple regression model in the sense that there's only one explanatory variable in the equation, and then if you use this ANOVA function and compare these models with the f-test, then this is a way of formally to test the statistical significance of the x2 in our model. And the end result is this case is like here. So the f statistics get a value like this, and p-value is this, and because the p-value is quite small, smaller than for example the classical risk level 0.05, so we would, I guess, reject the null hypothesis of x2 variable not needed in the model. That is, it is better to put in a model, and it gives us the more accurate after that way that we have both curve and height, we get a better estimates and better predicted values for the new observations. So that's pretty much it. That covers the introduction to statistic part. Obviously these regression models are quite advanced already, but quite easily, quite quickly, you kind of need these sort of models where there are not just one explanatory variable, but two or more explanatory variables in a regression model.